Okay, welcome back. This is now 9.7. Working with power series in general here. So before we worked with polynomials, and now we're working with these basically infinitely long polynomials, which we call power series. So what do they look like? They look like the following: the sum, they'll have some, coefficients, and then it will be centered around some point C, and going from 0 to infinity. And then, of course, it'll be something like a sub 0 plus a sub 1 times x minus c to the first plus a sub 2 times x minus c squared plus da da da. Okay? And eventually it'll be kind of a full circle thing where we'll connect these power series to the Taylor and Maclaurin polynomials that we saw in the previous section. Okay, but for now we want to just work purely with power series. We'll talk about their convergence, their divergence, and then we'll connect them to the functions that we're using that we wish to do approximations for. Okay, so in the previous section, the polynomials were connected directly to the functions, but here we've not made really that connection, and we just want to study them in their own right. Okay, okay, so we'll talk about their radius of convergence. Basically, where are they useful? Because ultimately, the power series will be used in place of functions sometimes. So they'll only be useful when we have a radius convergence. And there's going to be three types. The radius convergence is 0. In other words, it only converges when we're at the center, okay, where the point actually coincides. The point on this thing, C, actually coincides with the. Okay, so I'll just say this: the series converges only at the center. X equals C. The second kind of convergence, we have some sort of interval. Right? So we'll say the series converges inside this interval from around C, right? So inside this interval from C minus R to C plus R, and diverges outside of it. The endpoints will be a sort of a separate issue we'll have to investigate. So when C minus R is, when X minus C, sorry, is greater than R, it'll diverge. Okay, the last case is where it converges everywhere, and the radius on that guy will be infinity, so 2.3. The series converges absolutely for all values of the series converges absolutely for all values of X. Sorry, this should be absolute convergence as well. Okay. In order to figure out the radius convergence, we use the ratio test. Okay. So that's sort of our workhorse here. And so let's take a look. So there's example 2. We worry about the series from n equals 0 to infinity of n factorial times x to the n. Okay. So we'll look at the ratio test, take the limit of the absolute value of the ratio of a sub n plus 1 over a sub n. So a sub n plus 1 is this expression with n plus 1 in for n. And then all over a sub n. And we're going as n goes to infinity. We'll simplify this. N plus 1 factorial is the same as n plus 1 times n factorial. So you'll just have n plus 1 in the numerator. Likewise, then, x to the n plus 1 over x to the n is the same as x to the n plus 1 minus n. So we'll just end up with x to the first power in the numerator here, just 1 in the denominator then. With these problems, you want to factor out the x terms. So remember these limits, n to infinity, n to infinity. X is not in any way dependent on n, so I can factor that out of the limit. You have to include the absolute value symbol as you factor it out, though. So you have limit as n goes to infinity of n plus 1. Okay. And then this limit will go to infinity right here. And then if you multiply it by a constant, a positive constant, it'll still go to infinity. The only number that will work will be when x is 0. And in that case, you'll have convergence. So for this particular power series, its radius of convergence is this first case. So it's r equals 0. It's divergent everywhere except at 0. Okay. So anyways, this equals infinity, and we're going with the ratio test conclusions, right? So if r was less than 1, then it's absolutely convergent. 2, if r is greater than 1 or r equals infinity, it's divergent. And thirdly, if r equals 1, you have to try something else, right? So it's inconclusive in that case. And in particular, what we just found was the r value. Okay, so in this case, it equals infinity unless x is 0. So our radius of convergence, r, is equal to just plain old 0. Okay, let's continue on, look at all the other variations on this theme. So let's look at example 3 here. This time we have the sum from n equals 0 to infinity of 3 times x minus 2 to the n. Okay. So, right, you go to the ratio test, limit as n goes to infinity of the absolute value of 3 times x minus 2 to the n plus 1, all over 3 times x minus 2 to the n. Okay. 3's divide out. I have x minus 2 to the n plus 1 all over x minus 2 to the n. So it'll be x minus 2 to the n plus 1 minus n, which will just be x minus 2. Then you could factor that out in front. It's not dependent on n, so we can factor it out front. And you're just left with the limit of 1. The limit of a constant is a constant. So we'll have 1 times absolute value of x minus 2. Okay. Because this is our r value, we'll have absolute convergence when r, x minus 2, absolute value of, is less than 1. Okay. So in other words, x minus 2 here is less than 1 and greater than negative 1. And the radius convergence will just be half of this interval that's being created. So we have x less than, add 2 to all 3 sides, we get 3. Greater than 1. So the length of this interval is 2, and then divide it by 2, and that gives you the radius is 1. We still have to worry about the endpoints here. We don't know if those converge or diverge. That's in particular where the ratio test would be inconclusive. So sort of the capstone of this section would be kind of figuring out the convergence divergence at the endpoints, and you use all the tests from 9.1 and 9.6 to figure that out. So anyways, just one more example, the infinite radius, so it's convergent everywhere. You have the series n equals 0 to infinity of -1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. So end up being the Taylor series, or rather the Maclaurin series for the function sine of x, I believe. Okay, and it's actually convergent everywhere. We can use the ratio test to prove that. So r again equals the limit as n goes to infinity of the absolute value. So again, absolute value will negate these negatives to n or whatever. So you just throw them in the trash, and you're left with x to the 2n plus 2 plus 1 is 2n plus 3 all over 2n plus 3 factorial times the reciprocal of this stuff. So I'd have 2n plus 1 factorial all over x to the 2n plus 1. Okay. We can use the recursive rule for factorials to simplify this a bit, noting that 2n plus 3 factorial is the same as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Okay, so then we'd get that nice cancellation there. And then what's left over, I have x to the 2n plus 3 over x to the 2n plus 1. Subtracting exponents, I'll end up with just x squared. Okay. Of course, I'll factor that guy out front. I can see there's a cancellation there. I'm left with x squared times, and I don't need the absolute value because x squared is positive. So x squared times the limit of 1 all over 2n plus 3 times 2n plus 2. And then for all values of x, you'll have 0, because this will go to 0, and you'll just have whatever times 0, and that's always going to be 0. So here, our value is equal to 0. That leads us to the conclusion that for any x, this thing will be absolutely convergent. So hence, in this case, the radius of convergence is infinity. Okay. So then we need to go back to this example 3 and worry about these endpoints. So section 3, endpoint convergence. You need to do these separately. You sort of need to inspect them at their own. There's no pattern, right? If one endpoint is convergent, it's not going to imply the other endpoint is convergent. Okay, so the deal is, let's look at example 3 again, and we've already sort of started it. I noted the interval of convergence is going from 1 to 3, so the radius is half the length of the interval is just 1. Okay? I still need to check the endpoints, and what this is going to end up giving me is an interval of convergence. So endpoint convergence tells me the interval of convergence. Okay. All right, so you check x equals 1, and what you do there is literally plug 1 into this series for x. Okay, so what will that be then? We'll have the series 3 times 1 minus 2 to the n, which of course will be the series of 3 times -1 to the n. Okay. And then if you want to, you can consider that a geometric series. This is geometric with r equaling -1. Absolute value of r in particular equals 1, which is greater than or equal to 1, which is the defining characteristic of a series, geometric series that was divergent. Right? So hence it's divergent. The other thing you could do is an nth term test for divergence. The limit of this thing would go to 3 and -3. The even terms would go to 3. The odd terms would go to -3. So the limit of the terms of the series would not exist. Therefore, it's not equal to 0. Therefore, by the nth term test for divergence, or they say it's nth term test for convergence. I think they call it that. But anyways, regardless, it'll end up not being convergent. Okay, so there's x equals 1. X equals 3 is the same deal. You're plopping 3 in for x into the original series. So you have 3 minus 2 to the n. This will equal the sum of 3 times 1 to the n, which is just 1. And again, you could sort of say, let's do the nth term test this time. So note the limit of the terms of the series, in this case 3, equals 3, which is not equal to 0. So hence, by the nth term test for divergence, it diverges. I'll just call it the nth term test and say it diverges by that. Okay, so in these cases, these I didn't give you the interval of convergence yet. So the interval of convergence, I just call it IOC, is going to go from 1 to 3. Okay? So you indicate convergence or divergence with the parentheses or use the bracket. So if it had been convergent at 1, you would put a bracket and then 1 comma 3 open parentheses. Okay, so look at it. Well, let's look at a couple more, obviously, just to sort of iron all the issues out. Let's look at example 5 here. And we have the series x to the n all over n from n equals 1 to infinity. So again, you're going, you need to go to your ratio test first. So R is the limit as n goes to infinity of x to the n plus 1 all over n plus 1 times the reciprocal of this expression, which is n all over x to the n. That'll equal the limit as n goes to infinity of n all over n plus 1 times x. And then you could factor out the absolute value of x. So you get the absolute value of x times the limit as n goes to infinity of n all over n plus 1. The limit of that thing is just 1, so you end up with the absolute value of x. So by the ratio test, this thing is convergent when the absolute value of x is less than 1. And so we have x is in between 1 and -1 for absolute convergence. And the radius in that case then is 1. And we need to also then consider the endpoints for convergence or divergence. So first, x equals 1. Or maybe we should start on the other side. Let's do x is -1. So we have the series of -1 to the n all over n from n equals 1 to infinity. This is an alternating series, so you do the alternating series test. So note, firstly, the limit of the a sub n portion of the terms of the series is 1 over n, and the limit of that is 0. And then secondly, a sub n plus 1 all over a sub n. So we're doing a monotonicity test trying to decide if it's decreasing. So I get 1 all over n plus 1 divided by 1 over n, which equals n all over n plus 1. And obviously I have something smaller over something bigger, so that has to be less than 1 for n greater than or equal to 1. That'll work. Okay. So by the alternating series test, this thing is convergent. Just a side note, this is conditionally convergent, and it's often called the alternating harmonic series. Okay? Yeah, so on the other hand, you're going to get the harmonic series, right? So when x is equal to 1, you get the sum from n equals 1 to infinity of 1 to the n, which is 1 all over n. And of course, this is the divergent harmonic series. Okay, so at the end of the day, the interval of convergence then, the IOC, is going to be from -1 to 1. Let's look at another here. Example 6. what do we have? The sum of -1 to the n times x plus 1 to the n all over 2 to the n. Right. So again, ratio test, limit as n goes to infinity of the absolute value of x plus 1 to the n plus 1 all over 2 to the n plus 1 times the reciprocal of this, which is 2 to the n all over x plus 1 to the n. Right. Simplifying issues here, we get the limit of the absolute value of 1 all over 2 times x plus 1. Right. So the limit of this, basically it acts like a constant, so you just end up with the absolute value of x plus 1 all over the absolute value of 2, which is just 2. Absolute value of 2 is 2. So by the ratio test, this thing will converge when x plus 1 all over 2 is less than 1. Expanding this thing and multiplying out by 2, I get -2 less than x plus 1 less than 2. Subtract 1 from all three sides, -3 less than x less than 1. So our radius of convergence there is 2. And let's dive right in and determine the endpoint convergence. Okay, so first, x is -3. And I have the sum then of -1 to the n times -3 plus 1 to the n all over 2 to the n. Okay. So that'll be the sum of -1 to the n times -2 to the n all over 2 to the n. Okay, I'll rewrite this thing. It's the sum of -1 to the n times, I could rewrite -2 as -1 times 2 to the n all over 2 to the n. And then product to a power rule tells me this will turn into -1 to the n times 2 to the n, right? So this will be the sum -1 to the n times -1 to the n times 2 to the n all over 2 to the n. And then the 2 to the n's divide out. And finally, we're left with the sum of -1 to the n plus n, which is 2 n's. And that's equal to -1 squared to the nth power, which is equal to the sum of 1. Okay. Then by the nth term test, obviously, this thing will diverge. Why? It's because the limit of the terms of the series is equal to 1, which is not 0. Okay, okay, so that endpoint is divergent. And let's look at the other endpoint at x equals 1. So this time a little less work. -1 to the n times 1 plus 1 to the n all over 2 to the n. That's equal to the series -1 to the n times 2 to the n all over 2 to the n. And then the 2 to the n's cancel out, and you're just left with a series of -1 to the n. And again, by the nth term test, this thing is going to be divergent. Okay? If you'd rather, you can consider it a geometric series with absolute value of r is 1, so it's going to be divergent that way as well. But I like the nth term test. So by nth term test, the series diverges. And you have to say why. You can't just say flip a coin, and you have to give some reasoning. By nth term test, the series diverges because the limit of -1 to the n is going basically to -1 or 1. In other words, the limit does not exist. And of course, non-existence is not the same as 0. So by the nth term test, we can say it's divergent. Okay. Okay. What else we got? Okay. We're going to sort of develop the connection between the Maclaurin polynomials and our power series in a kind of a backwards way, right? We'll have some known power series just from the geometric series, And then we could take the geometric series and kind of integrate and differentiate it. More particular, we're going to want to integrate it in order to produce a power series for a function that would, we would want a power series for. In the beginning, the power series are kind of lame. So for example, the power series we'll initially work with is this power series. So one of the most cleanest power series, 1 plus x squared plus x cubed plus dot, 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 on and on forever. But the problem with this power series is it's kind of lame, right? I mean, I would rather work with this side than this side any day. So what's the deal? Why would I even care about something like this? It's because of its relationship to the integral of 1 all over 1 plus x dx, which is equal to the ln of the absolute value of 1 plus x plus c. In other words, if we could somehow take one of these lame power series that we all know about and integrate the thing, we would have a power series for the natural log just by integrating this polynomial. So we would hope that maybe somehow this was like this power series here, but integrated. So x plus, if I integrate this, x squared over 2 plus x cubed over 3 plus dot, dot, dot. And then we would have a power series for this guy, right? So obviously there's going to be some differences. There's some issues we have to iron out. Notice this is plus, this is minus. So this won't work exactly. We'll have to meddle with that. But the deal is differentiating and integrating. Can we produce new formulas from old power series just by doing that? And it turns out you can. Okay. So in particular, section 4 here, differentiating and integrating power series, it'll work, and the resulting power series has the same radius of convergence, but the endpoints may change in convergence. Okay, so integration and differentiation preserves radius of convergence. Okay, so there's kind of two ways you can do this. You can do it term by term, but can actually kind of take the integral of just the formula for the terms of the sequence as well. But you have to be a little careful because sometimes you'll lose terms when you do differentiation, right? So you'll annihilate a term and it'll go to 0, and so your summation index will be off. So what the heck does that mean? Okay, so let's start with P of x, our formula for a general power series, and I'll center it at 0 just for the sake of sanity. Okay. So what is this guy? It's a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus dot, dot, dot. You can take the derivative of this power series in two ways. You can either take the derivative of these term by term. So the derivative of a sub 0 is 0. The derivative of a sub 1x is a sub 1. The derivative of a sub 2x squared is 2a sub 2x, etc., right? What I'm also saying, though, is that you can just take the derivative of this with respect to x. Okay, so you can bring down the n, and I'll have n a sub n x to the n minus 1. But there's an issue, right? My index, I need to make sure that didn't change because here we lost this guy, right? So does it work? Can I put in n equals 0 to infinity and have it work out? And no, you can't, right? If you put in n equals 0, well, maybe you can. It would kind of work. But for this term here, but if it was 0 here, it would be 0, right? I don't know. I would say no. I would say no. We want to put this index at 1 at this point. Once we lose this initial term, we want to move this index over by 1. Okay. Okay, so anyways, uh, integrating, let's look at the integral version of this. It's the same idea. You could do it in two ways. You could integrate term by term. Okay, so the integral of a sub 0 is a sub 0 x. Integral of a sub 1 is a sub 1. Sorry, the integral of a sub 1 x is a sub 1 x squared all over 2, etc. Right? But you could also just do the integral of this expression with respect to x and have your answer. So the integral of that expression is going to be a sub n x to the n plus 1 all over n plus 1. And then again, the question is the index. Where do I start? In this case, you could just use the 0 place, and you want to make sure. So plug it in and see that this corresponds. A sub 0 x to the 0 plus 1 is 1, so I got x to the 1, and then it's all over 1. And then the next one, plug in 1, I get a sub 1, x to the 1 plus 1 is 2, so that worked. N plus 1, 1 plus 1 is 2. Okay, so it's working. One little issue, you do kind of technically have to put in an integration constant there, just to be safe. Right. So let's go through one of these problems. They can be a kind of long, so it'll give you basically 4 subsections for each question. This is example 8. We want to find the interval of convergence for the function, its derivative, and its integral. Okay, so for f of x, f prime of x, and then the integral of f of x. Okay. So our f of x is given as the series x to the n all over n from n equals 1 to infinity. Okay, so I'm going to find the interval of convergence for this guy, and then I'll know the radius of convergence for these guys, and all I have to do is check endpoints. Okay, so the interval of convergence for this guy. So we go with, well, let's expand it too, because we're going to be taking derivatives and integrals. So what is this? It's x to the 1 over 1 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. I think that's good enough. Okay. So doing the ratio test, r is equal to the limit of a sub n plus 1 divided by or multiplied by the reciprocal of a sub n. Okay, so of course that'll equal the limit of the absolute value of n all over n plus 1 times x to the 1. Factor out the absolute value of x. And you get the limit of n all over n plus 1, which of course is just the limit of n over n, which is 1. And so I got the absolute value of x. So that'll be convergent absolutely when that is less than 1. In other words, when x is less than 1 but greater than negative 1. That tells me the radius is equal to 1. I just need to check the endpoints. Okay? So when x is equal to negative 1, I have the series negative 1 to the n all over n. Oh, we did this one already, right? That's the alternating harmonic series, which is convergent. I'm allowed to do that. You're not. Please prove that these guys are convergent or divergent. Then on the other end of the interval x equals 1, I have the harmonic series, which is divergent. And again, you have to tell me why. Okay, so I'll write it out. Okay, it's the harmonic series. This one is convergent by the alternating series test. Okay, so at the end of the day, the interval of convergence for f of x is going to be negative 1 to 1. Okay, great. Now let's consider the variations on that thing. All right, so first let's look at the derivative of this guy. So f prime of x, I usually just work term by term. So the derivative of x is 1 plus 2x over 2, which is just x, plus 3x squared over 3 is x squared. Oh, this is a interesting guy, right? Plus dot, dot, dot. And then I'm also going to write summation notation just for good practice. If I took the derivative of this, it'd be nx to the n minus 1 over n. So that would leave me with x to the n minus 1. And I'm going to start at, well, you don't want to start at 0. Definitely not this time, because you would get x to the negative 1. So you want to start, I think, at 1. Yeah. Okay. So if I put in 1, I'd get x to the 0, which is 1. If I put in 2, I get x to the 2 minus 1, which is x. Okay, great. The interval of convergence then for this guy. So I know it has the same radius of convergence from -1 to 1, and I just need to check the endpoints now. Okay. So x equaling -1, I'll have the sum of -1 to the n minus 1 from n equals 1 to infinity. Note then the limit of -1 to the n minus 1 is going to go to either -1 if n is, if you're looking at the odd terms, or rather the even terms, it's going to go to +1 if you're looking at the odd terms, right? So that tells me the limit does not exist. Of course, it's not equal to 0 then, and so by the nth term test, it's divergent. Okay. When x is equal to 1, you have a similar situation. Just when you plug 1 in for x, you get the sum of 1 from n equals 1 to infinity. So again, we note the limit of the terms of that series, limit of 1 is just equal to 1, which of course is not equal to 0, which tells me it's divergent by the nth term test again. Okay. So in this case, the interval of convergence is just -1 to 1. Okay, last but not least then, we want to look at the integral of this thing. So we're looking at the integral of f of x dx. Going term by term, then I have x squared over 2 plus x cubed all over 3 times 2 plus x to the 4th all over 4 times 3 plus x to the 5th all over 5 times 4 plus dot, 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 plus c. Okay. Then in summation notation, you can, again, just integrate the term, this formula for the terms of the series, and you get x to the n plus 1 all over n plus 1 times n. Okay, and we're going from n equals, I think 1 to infinity will work. So I check, if I plug 1 in, I get x to the 1 plus 1, which is 2. Down here, 1 plus 1 is 2 times 1 is 2. Try n is 2. X to the 2 plus 1 is 3. Downstairs, 2 plus 1 is 3 times 2. Got it. All right. And then plus your integration constant. All right. Again, the radius of convergence is the same. It goes from -1 to 1. I just need to check the endpoints. So for x equaling -1, I get the sum of -1 to the n plus 1 all over n plus 1 times n. Right. This is an alternating series, so take the limit of a sub n. So 1 all over n plus 1 times n is clearly equal to 0. Secondly, then, the ratio of a sub n plus 1 is n plus 1 plus 1 plus 2 times n plus 1 times the reciprocal of a sub n, which is n times n plus 1. Clearly, n times n plus 1 will be less than n plus 1 times n plus 2. So we'll have something smaller over something bigger for n greater than or equal to 1. In other words, this will be less than 1, and by the alternating series test, it'll converge. Okay. On the other hand, then, when x is equal to 1, what do we have? We have the series of 1 to the n plus 1, 1 to the n plus 1, and 1 to any power is just 1, so we can just write 1 all over n plus 1 times n. Okay. This is equal to the series of 1 all over n squared plus n, which looks suspiciously a lot like the series of 1 over n squared, which is a p-series. So we'll do a limit comparison, limit compare with the sum of 1 all over n squared, which is p-series. P equals 2, which of course is convergent. Right? So we take the limit of the ratio of this thing and this thing. In other words, it's 1 all over n squared plus n times the reciprocal of this, which is n squared all over 1. And of course, its limit is just n squared over n squared, which is 1. Okay? So they both have the same behavior by the limit comparison test. In other words, both are convergent. Hence, the original series converges. Okay. So at the end of the day, for the integral, then, our interval of convergence, our IOC, is -1 to 1. Okay, that's pretty much it for this section, I think. Yeah. Okay, thanks for watching.